So, what is probability? Probability simply means how likely something is to happen. Whenever we're unsure about the outcome of an event, we can talk about the probabilities of certain outcomes. So what are types of probabilities? There are four main types of probability. They are classical probability, otherwise known as theoretical probability, axiomatic probability, subjective probability, and empirical probability. So what is the formula to get the probability of one event? The formula to calculate the probability of an event depends on the specific situation and the nature of the event itself. However, in general, the probability of an event can be calculated using the following formula. Probability of an event equals the number of favorable outcomes divided by total number of possible outcomes. This formula assumes that each outcome in the sample space is equally likely to occur. By dividing the number of favorable outcomes, or outcomes that satisfy the conditions of the event, by the total number of outcomes, you can determine the probability of that event occurring. It's important to note that this formula applies to situations where each outcome is independent and equally likely. In more complex scenarios, such as those involving dependent events or unequal probabilities, the calculation of probabilities may require different approaches and formulas. So these are all the formulas needed for different types of probabilities. There are many different formulas of probabilities for different situations. The most common ones are here. Classical probability is this one. The formula for classical probability, also known as the equally likely outcomes probability, is PA equals Fn, where PA equals classical probability, F equals frequency, or the number of favorable outcomes, and N equals number of total possible outcomes. Next is axiomatic probability. Axiomatic probability, also known as Kolmogov's probability, is based on three axioms, proposed by mathematician Andrei Kolmogov. The axioms define the fundamental principles of probability theory. The formula for axiomatic probability is not a single formula, but rather a set of axioms that govern the properties and calculations of probabilities. Here are the three axioms. The first is non-negativity axiom, right here. The probability of any event is a non-negative real number. That is, for any event A, the probability PA is greater than or equal to 0. So we get the equation PA is greater than or equal to 0. Next is normalization axiom. The probability of the entire sample space is 1. That is, if S represents the sample space, then PS equals 1. Lastly is additivity axiom. This is for any sequence of mutually exclusive events, A1, A2, and A3. The probability of their union is equal to the sum of their individual probabilities. That is, if AI and AJ are mutually exclusive and I does not equal J, then P times A union AJ equals P times AI plus P times AJ. Next is subjective probability. Now, subjective probability does not have a single formula, as it is based on personal judgments or subjective beliefs about the likelihood of an event occurring. Subjective probability differs from classical or axiomatic probability, which are based on objective criteria or mathematical principles. In subjective probability, individuals assign probabilities based on their own knowledge, experience, opinions, and subjective assessments of the situation. It does not follow a strict mathematical formula, but is more of a qualitative or subjective judgment. Subjective probability is often represented using a range from 0 to 1, where 0 indicates complete disbelief or impossibility, and 1 indicates absolute certainty or certainty. Probabilities in between 0 and 1 reflect varying degrees of belief or uncertainty. For example, if someone believes that there is a 70% chance of rain tomorrow based on their interpretation of weather patterns and historical data, and along with other factors, they are assigning a subjective probability of 0.7 to the event of rain occurring. In subjective probability, there is no universally applicable formula. Instead, probabilities are subjectively determined based on individual perceptions, opinions, and judgments. So, lastly, we have empirical probability. Empirical probability, also known as experimental or observed probability, is based on the relative frequency of an event occurring in a series of trials or experiments. So the formula for empirical probability is similar to classical probability. So the formula is empirical probability of an event equals number of times the event occurred divided by total number of trials or observations. So the probability of event E is found with the formula P E equals Fn, where F, however, instead of classical probability, is now the frequency of the event's outcomes of the event, E, and N is the total number of outcomes. So to calculate empirical probability, you need to conduct a series of trials or observations and count the number of times the event of interest occurs. Then you divide that count by the total numbers of trials or observations. So, for example, let's say you toss a fair coin 100 times, and you're interested in the probability of getting heads. If heads comes up 45 times out of the 100 tosses, the empirical probability of getting heads would be 45 out of 100, which simplifies to 0.5 or 45%, so 45 divided by 100. So to simplify, the difference between empirical formula and the classical formula is that F counts everything, counts all the trials, every time you get heads, right? So if you flip the coin, you get heads 45 times, you count all of the heads 45 times. But for F in classical, it is more of what you want. F is favorable outcomes. It's the outcomes that you want or the outcomes you're trying to find. So those are the differences between empirical and classical.
In probability, the set of outcomes of an experiment is called events. There are different types of events such as independent events, dependent events, mutually exclusive events, and so on. First of all, what are independent events? Two events are independent if the occurrence of one does not affect the chances of the occurrence of the other event. The mathematical function of the independence of events A and B is the probability of the occurrence of both A and B being equal to the product of the probabilities of A and B. Dependent events are two events are dependent when the outcome of the first event influences the outcome of the second event. The probability of two dependent events is the product of the probability of A and the probability of B after A occurs. The OR rule and the probability and examples. If we are interested in the probability of event A or event B occurring, we can use the OR rule. The OR rule states that we can find the probability of either event A or event B occurring by adding the probability of event A and the probability of event B, as long as both events are mutually exclusive. Finally, the AND rule. If we want to find the probability of event A and B both occurring, we can use the AND rule. The AND rule states that if event A and event B are independent, then the probability of event A and B happening is the probability of A times the probability of B.
So our first problem is roll one die and observe the numerical results. When S equals 1, 2, 3, 4, 5, 6, let E be the event that the die roll is a number greater than 4. So to solve this probability question, we need to find the probability of event E, which is the event that the die roll is a number greater than 4. Given that we have a fair 6-sided die, we know that each face has an equal probability of landing face up. So here, E equals probability of getting a number greater than 4. So therefore, there are a total of 6 equally likely outcomes in rolling the die, which are numbers 1, 2, 3, 4, 5, 6. Event E consists of the outcomes where the die roll is a number greater than 4, which are numbers 5, and 6. So there are two favorable outcomes in event E. Let's write that here. Two favorable outcomes. So to find the probability of event E, we divide the number of favorable outcomes, which is 2, by the total number of outcomes, which is 6. So here, we're going to have P E equals 2 divided by 6. The normal formula for this would just be P E equals number of favorable outcomes, so F, divided by total number of outcomes, N. This is known as classical probability. So if P equals favorable number of outcomes divided by total outcomes, which is 2 divided by 6, this is equal to 1/3, or as a decimal, it's 0.333 and onward, right? So therefore, the probability of event E, which is the event that the die roll is a number greater than 4, is approximately this, 0.33 onwards, or 33.33%. All right, so our next question is, an office employs 7 women and 5 men. One employee will be randomly selected to receive a free lunch with the boss. What is the probability that the selected employee will be a woman? So to solve the probability question, we need to find the probability of selecting a woman from the pool of employees. Given that the office employs 7 women and 5 men, there are a total of 12 employees. And the probability of selecting a woman can be calculated by dividing the number of women by the total number of employees. So this is another example of classical probability. P E equals F divided by N, favorable outcomes divided by total number of outcomes. And E equals chance of selecting a woman. So this is equal to the total number of women, so it's P equals the number of women, which is 7, divided by the total number of employees, which is 12. This gives us 7 over 12, which is also equal to about 0.5833. Therefore, the probability of selecting a woman as the employee to receive the free lunch with the boss is approximately 0.5833, or 58.33%. So our third problem is, what is the number of possible outcomes when rolling 2 dice? And make a diagram. So to find the number of possible outcomes when rolling 2 dice, we need to consider all the possible combinations of outcomes for each dice. When rolling a single die, there are 6 possible outcomes, right? Because there are 6 faces. 1, 2, 3, 4, 5, and 6. To find the number of outcomes when rolling 2 dice, we need to multiply the number of outcomes for each die, which is 6, for each die. And since there are 6 possible outcomes for each die, we multiply 6 by 6 since there are 2 die. So if this is 1 die, and right here, this right here is another die. So if there are 6 outcomes, we multiply it by the number of possible outcomes for the other die. So that is 6 times 6, which we get 36. So therefore, there are 36 possible outcomes when rolling 2 die. Now here's a diagram to represent the problem. So in the diagram, each cell, which is like one of these squares, represents a possible outcome. So for example, it's at the intersection of row 2 and column 3 represents the outcome of rolling a 2 on the first die, which is this, rolling a 2 on the first die, and rolling a 3 on the second die, resulting in a 5. So here we can see that there's 6 up here, 6 columns, 6 rows, multiplied by 6, we have 36 total outcomes.
So for the first question, 2 dice are thrown simultaneously. We have to find the probability of getting 6 as a product. So in this table resembles when 2 dice are thrown, and the possibility being 36 in total. So when you get 6 as a product is one number from the column times one number from the row equaling 6. So this is 6 times 1, 1 times 6, 3 times 2, and 2 times 3, which is 4 over 36 possible outcomes, which when simplified is 1 over 9. For the next one is getting the sum that is less than or equal to 3, which would be 1 plus 1, which is equal to 2, 2 plus 1, and 1 plus 2. Every other number here is more than 3. So this is 3 possible outcomes out of 36. When simplified, it is equal to 1 over 12. For the next one, getting the sum of 10, less than or equal to 10, which is all of the numbers here, less than this, which is equal to 12, and these two, which are equal to 11. That means that it's 33 outcomes out of 36 possible ones, which when simplified is 11 over 12. For getting a double means just when you get the same number twice for both dice, which is this column 1, 2, 3, 4, 5, and 6, which is 6 over 36 possible outcomes, which is 1 over 6 when simplified. And finally, getting the sum of 8, which is 6 plus 2, 2 plus 6, 5 plus 3, 3 plus 5, and 4 plus 4, which is 5, and 5 over 36. So for the second question, a lottery box contains 50 lottery tickets numbered 1 to 50. If a lottery ticket is drawn at random, what is the probability that the number drawn is a multiple of 4 or 5? So first we want to get the probability of both multiple 4 and of multiple 5 out of 50 lottery tickets. So to get that, we divide the total number of tickets by the 4, which is the multiple, to get the probability out of 50 to get a number that is a multiple of 4. And then we do the same for 5, which we then get 10 possible outcomes out of 50 lottery tickets. The OR, in this case, it's a rule in probabilities. The OR rule states that we can find the probability of either event A or event B occurring by adding the probability of event A and the probability of event B, as long as both events are mutually exclusive. So in this case, we can just replace A and B for 12 over 50 plus 10 over 50, which gives us 22 over 50 possible outcomes. So for the last question, a magician takes out 2 cards from a deck of cards, one after the other without replacement. What is the probability of getting an ace of spade and a card of heart as the first and second card respectively? To solve this problem, we need to determine the probability of drawing an ace of spades as the first card and a card of hearts as the second card, one after the other. A standard deck of cards has 52 individual cards. The probability of pulling an ace of spades out of this is 1 out of 52. After pulling this ace of spades, the total number of cards reduces from 52 to 51. And then the probability of pulling a heart from this is 13 over 51. We can use the AND rule in this situation, which is the probability of A and B happening is equal to the probability of A times the probability of B. So it's 1 over 52 times 13 over 51, which is then equal to 13 over 2,652. In decimal points, it's 0.0049, and as a percentage, it's equal to 0.49%.